Good morning, dear students. In this session, we are going to learn about structure of sodium chloride, potassium chloride, and cesium chloride, and also we are going to discuss about defects in crystals. The contents of this sessions like this: structure of sodium chloride, potassium chloride, and cesium chloride, defects in crystals. In that, we are going to learn about stoichiometric defects, in that Schottky defect, Frankel defect, and non-stoichiometric defects, in that metal excess defect and metal deficiency defect. Structure of sodium chloride and potassium chloride. First one, structure of sodium chloride. Sodium chloride as a FCC structure, that is phase center cubic lattice structure. Here the sodium atoms are present in the octahedral voids in CCP. CCP is nothing but a FCC, that is cubic close packed system. Here each chlorine atom, you can see the chlorine atom here, it is surrounded by 6 sodium atoms. Similarly, sodium atom also surrounded by 6 chlorine atoms. So the structure is referred to as 6:6 coordination. Therefore, the coordination number of sodium chloride is 6. And the radius ratio of this sodium chloride is 0.5 to 5. Here a single unit cell of sodium chloride has 4 sodium and 4 chlorine ions. So coming to the calculation part of number of sodium ions, it is calculated by 12 at corners into 1/4 plus 1 which is present at the body center. So totally it is 4. When we solve this, you will get a 4. Similarly, for chlorine ions, number of chlorine ions, here we have 8 at corner. So it is divided by 1/8, that is 1/8 into 1/8 plus 6 at phases into half. So it is also gives 4. So number of sodium chloride units per unit cell is 4. So similarly, the structure of potassium chloride also same as that of the sodium chloride crystal. Coming to the structure of cesium chloride. Here in the cesium chloride structure, chlorine ions are present at the corner and cesium ion is at the center, or vice versa. It may be a reverse. So in this structure, cesium chloride has cubic unit cell structure. Coordination number for this type of ions is 8 and the structure is referred to as 8:8 coordination. In the previous sodium chloride, it is 6:6. Each cesium ion in this structure touches 8 chlorine ions. You can observe in this structure, and each chlorine touches 8 cesium ions. So radius ratio of this cesium chloride is 0.732. So coming to the number of chlorine as well as cesium ions, here chlorine ions is calculated by 8 at corner into 1/8 in which it touches, so that it will give 1. Similarly, cesium ions is calculated as 1 into 1. 1 at the body center into 1. So it also gives 1. Therefore, number of cesium chloride units per unit cell is 1. Defects or imperfection in solids. See, an ideal crystal is one which has the same unit cell containing the same lattice points throughout the whole of a crystal. This is what an ideal crystal. So this ideal crystal is possible only at zero temperature. So other than this zero temperature, certain irregularities are observed. So on increasing the temperature, the chances for an ion to escape from the lattice site and thus to create a vacant site. This is what is called as defect or imperfection in crystal. Imperfection or defects in crystal can be classified into two types. One is point defects and another one is line defects. What are these point defects? The defects which arise due to the irregularity, missing of ions, displaced or extra ions from ideal arrangement of atoms around a point or an atom in crystalline substances are what is called as point defects. Coming to the line defects, what is this line defects? The defects which arises due to the irregularities or deviations from ideal arrangement in entire row. In entire row. So this is what is called as line defects. And again, point defects are classified into two types. One is stoichiometric defect and non-stoichiometric defect. And again, this stoichiometric defect classified into four types, that is vacancy, Frankel-Schottky defect and interstitial defect. And these non-stoichiometric defects are classified into two types. One is metal excess and another one is metal deficiency. Let us discuss these defects in detail one by one. First one, stoichiometric defects. What are these stoichiometric defects? The stoichiometric defects are nothing but defects when a number of positive and negative ions are exactly in the same ratio as shown by their chemical formula. They obey the law of constant composition. What is that law of constant composition? It states that the same chemical compound always contains the same elements in the same composition by weight. This is what is called as law of constant composition. Again, these stoichiometric defects classified into two types. One is in non-ionic solids and in ionic solids. These are in non-ionic solids. These are two types. One is vacancy defect and another one is interstitial defect. In ionic solids, one is Schottky and another one is Frankel defect. Let us discuss these defects in detail. What is vacancy defect? When some of the lattice sites are vacant, you can observe in this picture, the crystal is said to have vacancy defect. Here you can see that some of the lattice are vacant here. These are the unoccupied positions are called vacancies. So what happened to the density in this case is it is decreases in vacancy defect. What about interstitial defect? When some constituent particles, that is atoms or molecules, occupy a vacant interstitial positions. You can see particle occupy the vacant interstitial position in the crystal lattice. In crystal. So the crystal is said to have interstitial defect. What happened to the density in interstitial defect? It increases because particles are occupied in the interstitial places or a position. So obviously the density increases. Coming to the Schottky defect. What is this Schottky defect? When equal number of cations and anions are missing from their normal lattice sites. So, the formation of a pair of holes takes place. It is what is called as Schottky defect. See, in this Schottky defect, increase in the volume of the crystal takes place with no increase in its mass. As a result of a formation of a pair of holes, what happened? Density as well as covalent character of the crystalline solid decreases. And missing of cations are equal to the missing of negative ions here. So the crystal as a whole can be treated as a electrically neutral. Why? Because here the missing of cations and anions are same. So the crystal is electrically neutral. And this type of defect is generally observed in strongly ionic compounds with high coordination number, having cations and anions of almost similar size. Example for this Schottky defects are sodium chloride, potassium bromide, cesium chloride and silver bromide. You can observe in this picture, that means the missing of cation as well as anions takes place. That is equal number of cation as well as anions takes place. See, in the second row missing of cation and in the last row missing of anion takes place. That is cation vacancy and anion vacancy. Coming to the next defect, important defect, that is a Frankel defect. What is this Frankel defect? Here, when shifting of cation or anion from its normal position to its interstitial site, you can see the picture here. Interstitial site between the lattice points, this defect arises. So that is Frankel defect, and this defect is also known as dislocation defect. The reason for occupying a interstitial by a cation. See, you can observe here the cation occupying in the interstitial position and not an anion. It's because the size of cation is smaller than that of an anion. Example for this kind of defect is a zinc sulfide and silver bromide. That is what happened regarding smaller and bigger ions. In zinc sulfide and silver bromide, the Zn2 plus and Ag plus ions occupy interstitial position and leave behind a hole. Such defect increases with increase in temperature. In this defect, that is a Frankel defect, the density is unchanged and the dielectric constant here, what happened, it increases. So presence of holes, the stability of the crystal decreases here. Because of the presence of holes, the stability of the crystal decreases. And where we can observe this defect means the defect is generally observed occur in a compounds having low coordination number and anions having much larger size than the cations. Say for example, silver chloride, that is AgCl, AgBr, AgI, ZnS, etc. Difference between these two defects, that is Schottky defect and Frankel defect. First one, Schottky defect. In Schottky defect, here it's shown by a ionic solids containing similar sized cations and anions. So what happened in Frankel defect, it's shown by ionic solids containing large differences in the size of ions. Second point, in Schottky defect having high coordination number, here in Frankel defect having less coordination number. Third point, an equal number of cations and anions are missing to maintain electrical neutrality in Schottky defect. The defect which is arises in a crystal, that is a Schottky defect, the crystal is electrically neutral. What happened in Frankel defect? It created when the smaller ion is dislocated from its normal site to an interstitial site. Next point, decreases the density of the substance. Here in Schottky defect, because of this defect, density is decreases. What happened in Frankel defect? There is no change in the density of the crystal. It creates a vacancy defect as well as interstitial defect. Frankel defect creates these two. Example we have already discussed, and one important point we can observe here, that silver bromide shows both Schottky as well as Frankel defect. Coming to the non-stoichiometric defects. Till now we have discussed about the stoichiometric. Now let us see the non-stoichiometric defects. See, non-stoichiometric defects arises when the number of positive and negative ions present in the compound are not in the same ratio. What happened in the stoichiometric? They are in the same ratio. Here they are not in the same ratio. Such compounds do not obey the law of constant composition. And these are of two types, depending upon whether the positive charge is excess or negative charge is excess. These are metal excess and metal deficiency defects respectively. Let us see the first one, that is metal excess defects. These defects are point defects in non-stoichiometric crystals which arise due to the excess of positive ions. Here the excess of positive ions are there. So these are called as metal excess defects. And this defect arises in two ways. One is anionic vacancies and another one is cationic vacancies. Anionic vacancies. Here negative ions may be missing from their lattice sites in anionic vacancies, leaving a hole. You can observe here negative ion is missing, so that leaving a hole which is occupied by an extra electron. That hole is occupied by an electron to maintain the electrical neutrality, and it is similar to Schottky defect. But what happened? It differs in having only one hole. What happened in the Schottky defect? We have two holes. The electrons trapped in anion vacancies are referred as F centers. These are called as F centers. Next one, cationic vacancies. An extra positive ion, what happened in this cationic vacancy means an extra positive ion may also occupy an interstitial space in the lattice, and to maintain electrical neutrality an electron is also present in the interstitial space. You can observe here one positive ion occupied at the interstitial position. So in order to maintain the electrical neutrality, an electron is also present here. So it is similar to Frankel defect but differs in having no holes. Here there is no hole, and in having interstitial electrons. This defect is much more common. Coming to the metal deficiency defects. When a cation is missing from its lattice site and the adjacent metal ions acquires higher oxidation state. You can observe here adjacent ion acquires higher oxidation state. The defect is called as metal deficiency defect. This defect arises again in two ways. One is cation vacancies and another one is anion vacancies. See what happened in cation vacancies. Here positive ion may be missing from its lattice site and extra negative charge is balanced by an adjacent metal ion having two positive charges. You can observe that cation having +2 charge here instead of 1 in order to maintain. So this defect is generally shown by the compounds of transition metals. Next one, anionic vacancies. In second picture you observe here the negative ion may find an interstitial position. You can observe one ion which is find a position in the interstitial, and the charges are balanced by means of an extra charge on an adjacent metal ion. Negative ions are usually large, but it would be difficult to fit them into an interstitial position. So coming to the revision of this session, today we have discussed about the structure of sodium chloride, potassium chloride and cesium chloride, and we have also discussed defects in crystals. In that we have discussed stoichiometric defects and non-stoichiometric defects. Under stoichiometric defects we have discussed SCHOTTKY defect and Frankel defect. In non-stoichiometric defects we have discussed metal excess defect and metal deficiency defect. These are some of the references I referred for this session. Thank you.